Our next expert on the future is David Yu from the geospatial firm Esri in Redlands, California, where he is a data scientist in their Geo AI division. His presentation is See What Others Can't, Deep Learning in Arcgis.
Hello everyone. Thank you for attending this session. Today we will be talking about See What Others Can't using deep learning in ArcGIS. First off, a little bit about myself. My name is David Yu. I'm a data scientist on the Geo AI team here at Esri. My background is in computer science, whereas Esri had traditionally been a GIS company. And what that means is I spend a lot of my time trying to bring the latest and greatest tools and technologies, processes, and practices from the world of machine learning to solve real-world GIS problems. And in particular, I work on things like object tracking and anomaly detection, pattern analysis, and more recently, generative networks. And before I dive into some examples, I'd like to first take a quick step back and address some fundamental definitions. And we start off with artificial intelligence. So we've all heard about AI, it's really become this buzzword in recent years. But how do we define AI in the context of solving a real problem like disaster response, say? And how do we quantify the effect of its application? And what do we mean by a AI-enabled workflow? So technically speaking, AI is a paradigm of computing to get machines to perform tasks at the level of a human, if not better. Whereas machine learning is a specific implementation of AI that's all about learning from large quantities of data in order to derive rules and recognize patterns without being explicitly programmed to do so. Deep learning, on the other hand, again, is another term that we're starting to hear a lot nowadays. It's all about leveraging the power of the deep neural network. And what that allows you to do is analyze high dimensional data, so things like images and videos. We are concerned mostly today with deep learning and its application to extracting insight from imagery and vector data. And in particular, we will be leveraging the ArcGIS ecosystem, which sits at the intersection between machine learning and deep learning. So the first example I'd like to dive in straight away here is accidents prediction. And if you're familiar with machine learning, this is not an uncommon workflow. Basically, the central question that you're asking is, can we predict the risk of a car accident along roadways? And if you think about it, there's really tens of variables at play here. So first of all, there is temporal factors like what is the time of the day, what is the day of the week, and also weather patterns, things like if there's any kind of snow coverage on the road, as well as spatial factors. So things like if there's any curvature on the road, how far is the accident away from an intersection, and so on. So really there's tens of variables, and it's impossible for a human to be able to understand what is the precise combination of each one of these variables that may lead to a higher risk of an accident. So this is really where machine learning would be able to help by analyzing this high dimensional data. However, what people don't realize is just how much insight a GIS-centric approach brings to the table. So in order to motivate this, I have a link here to a story map on the impact of geographic considerations towards accidents risk. So when we consider a problem like this, let's first think about what factors definitely contribute to the likelihood of an accident. How about the number of cars on the road? Obviously, this type of data is going to be a little bit difficult for us to come by, especially if we're thinking about collecting highly granular data at regular intervals, perhaps in real time. However, for our purposes, it's going to be good enough for us to make use of something much simpler. Let's say a population density layer that's going to be a good enough proxy for us to understand the number of cars on the road at any given time. Something else that we might want to consider are the various physical attributes of a stretch of road. So let's say we have a road here that I can kind of pan around and play around with. And let's say we have a good understanding of some of the physical attributes like the number of lanes on that road, what is the surface type of that road, what is the speed limit that's been imposed on that road, and so on. So why is geographic context important in this situation? Well, let's say we have this road versus some other road that has the same physical attributes. So let's say for the second road, it has the same number of lanes, it has the same speed limit, it has the same surface type, and so on. Well, how can we differentiate the two? Well, we can do so by bringing in additional contextual information, let's say geographic context. And if we place this in geographic context, we can see immediately that the second road kind of hugs along a mountainside and has a steep drop off to one side and perhaps some obstruction on the other side that prevents the driver from looking across here. and this may raise the likelihood of an accident, versus the first road, which lies in a flat plain with good visibility on both sides, and you can very clearly see that it's going to be pretty difficult for you to have an accident here. So this is why geographic context is important. So let me show you some of the model results that we have. So here is running a model within ArcGIS Pro, and specifically we're using the scikit-learn library, and we are using XGBoost to understand what is the level of risk on a per road segment basis. So you see all of these road segments are color coded, and they have been color coded according to the risk that's assigned it by the model. So green obviously represents low level of risk, whereas orange and red represents regions of high risk. And we can see these red dots here that correspond to locations where accidents actually happened. And we can see that they essentially just lie on road segments that the model has predicted high likelihood of an accident for. And coming back to the point of GIS, what ArcGIS allows you to do is to be able to perform this type of end-to-end analysis very seamlessly. So it's essentially a framework for you to perform data collection, measurement, visualization, analysis, planning, and finally turning that data into actionable insight. All of that is available within ArcGIS. And from a deep learning perspective, here are basically the 4 key imagery tasks that you can perform with deep learning in ArcGIS. So first of all, we have pixel classification, and in the world of machine learning, this is also known as semantic segmentation. This is basically the task of assigning unique values, class values, on a per pixel basis. Then you have object detection, which is all about returning that minimal bounding box or minimal bounding polygon over objects of interest. Then you have instance segmentation. So those of you familiar with something like MassCar will recognize that that's an instance segmentation workflow. So this basically combines the best of both worlds between object detection and pixel classification. One of the shortcomings of pixel classification is, if we look at the example over here, we see that some of those houses, even though that they've been, very successfully segmented out, they're kind of joined together, and the model has no way of knowing what are unique instances of a house. So that's where, you want to be able to segment out also those unique instances, and that's where instance segmentation can help. And then finally, you have your sort of standard machine learning, 101 model that allows you to be able to perform image classification. Now, the second demo I want to talk about is AI for disaster response. This is a project that we started off back in 2018 in October, essentially in the wake of Hurricane Michael. So for those of you who know, Hurricane Michael is kind of the worst natural disaster that happened in recent memory. It's something that made landfall in Tyndall Air Force Base in Florida, and it caused immense amounts of damage. So it had a maximum sustained wind speed of about 155 miles an hour, which basically makes it a Category 4 storm, very, very close to Category 5, and it essentially nearly leveled the entire Air Force Base in a matter of minutes. So unfortunately, disasters like this are becoming very, very common nowadays, and coordinating a response is becoming challenging in a number of different ways. Usually following a disaster like this, either a hurricane, earthquake, or flooding, certain agencies will go out and fly aircraft in order to capture a bunch of imagery in the area to be determined, in order to determine the level of damage. But all of that imagery needs to be processed somehow, and the way that this is usually done is that analysts would essentially sit down and manually comb through these hundreds and thousands of images in order to circle out locations where structures may be damaged or roads may be blocked or have debris on them. And unfortunately, this takes a lot of time as well as effort in a situation where you don't have all the time in the world. So this is where we see an opportunity for parts of this workflow to be automated by AI. So our workflow is broken down into 4 pieces. First, we want to understand which structures are damaged. We want to know where people may be trapped and may need rescue. And we also want to understand if there's any spatial patterns, such as any clustering behavior for this type of building damage. And if there's any kind of hotspot, then we can isolate it and really prioritize rescue in those locations. So we first trained 2 AI models. one model in order to identify building footprints in an area of analysis. And the second model we ran on top of the output of the first model in order to classify them as either damaged or undamaged. And to show you what that labeling workflow looks like, this is it. Essentially, this is a web app that we've created. We understand that labeling is a very time-consuming task, and it's definitely not something that a single person wants to do. So that's why we created this web app for all of us in the office to be able to collaborate. We can have multiple people work on this at the same time. And we see that there is an underlying built-in footprint layer already, and in order to label it, it's very simple. We can just click on it and select from a drop-down menu whether or not it's damaged or undamaged. Of course, if we don't have access to an underlying building footprint layer, we can also just draw bounding boxes as well through this web app. So the second model that we've built is for detecting damaged roads. It's not enough for us to know which buildings are damaged. We also want to know what is the best way in order to route first responders to regions where people may need help. And that's where the second model comes in, because we want to know if there's any debris on the road, if roads have cracked, or if roads are completely washed away, and so on. So again, we are training an AI model in order to detect road debris. And this AI model trains very similarly to the previous models for building footprint detection and for damage detection, except in this case, we're detecting road debris. And again, this is a case where high quality, high volume training data would be needed. And again, we've built out a web app that does just this. So we can see that you can click on a segmented road and you can kind of assign it what is the level of damage and so on. So all of the training is done completely within the Arcgis platform, and this is the type of output that you can get. So now we see that the model is predicting that these regions have blocked roads or damaged roads. We can kind of switch back and forth in between them in order for you to see that, yes, these are indeed locations where either trees have fallen down or if there's any kind of random debris on the road. And then the next piece is what I've talked about, and that is optimal routing. So we want to understand not only the location of damaged structures, not only which roads are passable, which ones are impassable, but we also want to automatically and intelligently route first responders from, let's say, their forward operating base to locations where people may need help. And in this case, we are using the Arcgis Network Analyst extension in order to perform the routing task. So in this case, we've assigned a forward operating base to a local fire station here. And you see over here, these are the damaged structures. So, these red buildings, these red boxes represent damaged buildings. And by running all of this through Network Analyst, it's going to return the optimal route for us to, route these first responders to those locations. And then the last piece of this equation is getting this information into the hands of the people who are going to use it. So we utilized two things. First, we utilized Arcgis Workforce, which is a mobile solution from ArcGIS. We also are utilizing the Arcgis Operations Dashboard, which is essentially an end information product that allows us to be able to visualize some of this data. So first of all, the Arcgis Dashboard, in this case, we've created something like a situational awareness dashboard that allows us to be able to see what is the level of damage for buildings and roads. And we also can, see a breakdown of what is the level of damage in this area of analysis, right? So for the current extent on the screen, we can see that, what is the severity of the building damage, what is the rough cost that's been incurred by the storm on this area, so the average damage per building, as well as, what is the number of damaged roads and what is the number of damaged buildings. And the other part is an internal dashboard that's kind of exposed to analysts. So now someone at HQ who's, let's say, monitoring this response would be able to keep up with live progress updates from all of the first responders from out in the field. And we can kind of see, the same information, but we also have access to information like what is the location of all of those operators out in the field, what is their current task, and what is their level of completion of the current task. Let's say, if they're rescuing somebody. And then finally, just to conclude on some very cool visuals, following this successful project, we also collaborated with Microsoft and brought this workflow into Azure Stack Edge, which is basically their edge device. And this piece was actually presented at the Microsoft Ignite conference in 2019, where we showcased the same damaged outputs, but now in a 3D scene, which I think also attests to the versatility of the ArcGIS platform. And here's kind of that final 3D scene output. So here are some additional resources to learn more if you're interested. And thank you for listening to my presentation today.
Thank you, David. That was really great. We do have a few questions. We have about 5 minutes for questions, so we'll dive right in. First, we'll start with a lot of the folks who are sitting in the audience today might not necessarily be geospatial people, but might be quite intrigued by deep learning for geospatial. So could you just maybe fill people in on what type of educational background they might need to get into something like this?
Sure, sounds good. So, as I've mentioned, my background is in computer science. So you definitely don't need to have a PhD in GIS in order to, build models for geospatial context. Really, it's more background knowledge would be useful. So, for instance, there's a bunch of openly available courses online that you can take about GIS, just to get you familiar with some of the basic concepts like, what is a feature layer, what are feature classes, and how do you do, let's say, analysis after your models finish running inference. And there's also actually a bunch of open source tools available if you're interested in exploring things like GDAL in order to basically understand how to bring in like a feature layer into your workflow. So really, most of the background I would say is in computer science and in data science. And as you know, there's tons of data science resources out there. So really, the GIS component is really in post analysis and in pre-processing.
All right, thanks. We've had a few questions related to natural disasters, and you mentioned in the presentation about hurricanes. Well, we're all sitting here, many of us are in Fort Collins, a few miles away from the state's largest fire. You're in California, where there's fires everywhere. How is this being used for either managing or preventing fires or assessing damage? And have you noticed a trend over time where this is being used more to turn around information more quickly?
Sure. Yeah, that's a very good question. Definitely, I see a lot of use for managing a response. It's going to be a little bit more difficult in order to build out a model to perform pure prediction. So to some degree, we can use historical data in order to fit a model on things like hurricane tracks, things like floodplains and fault lines in order to predict the possible impact zone of a disaster. But overall, it would be kind of difficult to predict the occurrence itself. Um, the best thing that we can do is try to minimize the amount of damage that's been caused post-disaster by trying to automate the process of detecting locations where damage has occurred, or by prioritizing regions where people may need help and the first responders should be sent to. And yes, definitely we're seeing a lot of uses for this. For things like fires, machine learning is being used today to assess potential fire risk by analyzing information like NDVI indices, or by analyzing land cover classification. Typically, if you have, let's say, a mountainside that has a lot of vegetation growing, that's a red flag that potentially a fire could start here. So yeah, it's being used a lot nowadays.
Okay, and all of this is dependent on imagery. So have you noticed a trend, or is it hopefully going to get to a shorter turnaround time, so that basically how long does it take from the time imagery is taken from the time results can be developed, like building damage?
Sure. So typically, for especially for new imagery that's coming in, and if it's over a location where your model has been trained before, you would need to perform some kind of model fine tuning. So the idea is, if you have access to a pre-trained model, let's say for building damage detection, that already is 80% of the work done. And then all you would have to do is spend a little bit of time to label over the regions where the new disaster has occurred, and then to fine tune your model, to retrain your model to get from that 80% to the 100%. And that depends. Honestly, it's I can't give you a single number on how long it would take, but typically it would be a couple of days. However, if you take into account how this has been traditionally done, is people are manually sitting down and labeling out regions where damage has occurred. That could take far longer, especially if you're talking about a disaster that has impacted multiple states. So really, If you have a model already trained, then to perform inferencing, it could be just a matter of hours.
Okay. And you mentioned this idea of time and how long it takes to get information. What about the idea of crowdsourcing? Is that a potential and viable and reliable option?
It's a potential. In terms of viability and reliability, that's, I think, where the problem comes in, because especially for all of these deep learning models that we're building, we're realizing that you can have a half decent model, but if you don't have access to high quality training data, if there is no QA QC process attached to that, to the way the training data is being generated, it doesn't really matter how good of a model you have, the output is going to be pretty garbage, right? So it's garbage in, garbage out. So crowdsourcing is possible, but then we would have to figure out a way to still manually sit down and comb through that data to make sure all of the data is valid.
Okay. And I think that's all we have time for. All right.
Cool.
Thank you so much, David. There were a couple of questions in the Q&A that we didn't get to, but we can answer those just by typing them in. Thank you so much.
Thank you.